Now we have Gabi Sato-Polito from IAS talking about the novel PTA results and what's weird with the PTA result. Have you done this, bro?
Yeah. Yeah, maybe. Yeah, so I'm going to talk about the recent results by pulsar timing arrays, and particularly in light of supermassive black holes and what we're learning about them. So I'll start with the general introduction about how this works, what are pulsar timing arrays. Then I'll move on to what are the most likely sources for pulsar timing arrays, which are supermassive black holes, and kind of put this into the context of what we already know about supermassive black holes. And then I'll talk a little bit about what I think we're learning about from this measurement. So given that this has now been observed, what does this mean? And I'll focus on these two papers in the bottom, which were done in collaboration with Matthias Saldarriaga and with Elio Quadert, where basically we compare these observations to predictions from based on electromagnetic observations of supermassive black holes. And we point out that there's kind of a simple way to interpret what the amplitude of a stochastic background produced by supermassive black holes should be, and that this seems kind of lower than what PTAs currently measure. I'll then talk a bit about a more detailed statistical modeling of the distribution of the characteristic strains that we expect to see given these types of sources, and the fact that you can have Poisson fluctuation in the number of sources, and that this allows us to already get some constraint on the typical number of sources contributing to the background. So even though PTA measurements are not currently the pinnacle of precision, there's still a lot of information we can get out of them with relatively simple theoretical tools. So the kind of general idea of pulsar timing arrays is that we have pulsars in the galaxy, which are these spinning neutron stars with jets that may be pointed slightly off axis. So have this lighthouse model of pulsars. So you have some neutron star, some jet, and as it's spinning around its axis of rotation, every time this jet faces the observer, you see a little blip, right? So as you're observing this over time, you're going to see a periodic blips whenever this jet faces us. And this is to record this arrival time of pulses over here. And these periods are roughly of milliseconds, millisecond periods. These are millisecond pulsars. If you want to see a more realistic rendition of what these pulse profiles look like, you can look at Howe's t-shirt. Joy Division. Anyways, yeah, so this is basically what you observe, and the arrival time of these pulses gets perturbed by metric perturbations. So these will alter the arrival times of your pulses. In interferometers, you usually quantify this in terms of the change of the length of the arm of your interferometer. Here you're measuring arrival times, so you're measuring the shift in time over time. So the equivalent kind of order of magnitude estimate for how well you need to do this that you could do for pulsar timing arrays is basically that your strain for the sources that you typically expect to observe is roughly 10 to the minus 15, let's say, that's your target. And what you're measuring, this needs to be equal to the deviation in the arrival time of your pulses. So you're recording repeated arrival times of pulses, and the deviation over the total observing time of your pulsar needs to be of this order. You observe these pulsars for roughly 10 years, and 10 years is 10 to the 8 seconds. So the delta t that you need to see is 10 to the minus 7. So it's say 100 nanoseconds. So you need to be able to tell. You need to have a deterministic model for your pulsar, and you need to be able to tell that it arrived late or early by about 100 nanoseconds. That's what you need to measure gravitational waves with pulsar timing arrays. So the fact that this is possible at all is pretty amazing. These are really difficult measurements, but it's very impressive that people can do this. atomic clock errors are a non-negligible part of the error budget for these instruments. Like it's pretty insane. Okay. So more quantitatively, right, the idea is that you can look at all of these pulsars across the galaxy, you record all of these, and you will try to infer these gravitational waves from that. You can define the timing residual of pulsars, which is this relative shift in the period of the pulsar over time. And basically, if you have a gravitational wave traveling in this omega hat direction and some pulsar A in p hat direction, this timing residual will be equal to the difference between the metric on Earth and at the pulsar, and essentially projected along this Earth pulsar axis. And this is the observed timing residual.
Sorry, I've misunderstood. It's an indirect detection of gravitational wave, right?
What is direct or indirect? I mean, the presence of a gravitational wave is altering the arrival time of your
But
pulse.
you're not
So is that
detecting the gravitational wave.
I mean, you're detecting it as well as you would detect with any interferometer, right? You're measuring
an electromagnetic signal.
of the pulsar, but it's the same way that you're measuring the shift, like you're sending light in an interferometer and then combining it afterwards, right? You're detecting volts or something.
It's like the Higgs boson.
No, here you're not measuring the orbital decay of a binary pulsar. You're not in that case, you have a binary and you're observing the orbital decay of that binary. Here you're observing a pulsar and you're just seeing the fluctuations in the arrival time of your pulses from some external gravitational wave changing the metric on Earth and at the pulsar. It's as direct or indirect as an interferometer.
It's not the same as light.
No, it is.
It is.
It is.
Okay, so since this came up yesterday and you've pretty much seen this exact slide in Ricardo's talk, you can basically, the regime that we think we're operating in is in this stochastic background limit. So what does that mean? One thing you can do is that you can take the timing residual that I showed before and you can expand your metric into plane waves. Here we've absorbed all of these dependencies in the direction of the pulsar and your polarization tensors and so forth into this antenna beam pattern. So this is pretty much the same thing that we discussed yesterday for PTAs. And so FA is the antenna beam pattern for pulsar timing arrays. So you can think of this in terms of like an individual source producing a single propagating wave, or you can think of this as waves from every direction, omega hat here, that you're integrating over, so over every direction. And I guess the way I would phrase the difference between, since this came up, between the individual source and the stochastic background is basically that for the individual source, you have a very deterministic prediction of what your gravitational wave should look like. Like you can model the waveform of a binary as a function of some set of parameters. But suppose your background is produced by many sources, say 1 million sources that are all equally important. You're not going to describe, the individual parameters of 1 million sources. And so a stochastic background is basically what you do when you've given up on that idea, where instead of trying to model each source individually, you're now saying you're just seeing the incoherent superposition of all of them, and you're going to treat this as a stochastic field and just try to infer its statistical properties. Since it's just a sum of a bunch of waves, the mean is 0, and the first non-trivial moment that you can try to measure is the variance. Yeah.
But there is an assumption that these are coherent waves, right? I mean, you have frequencies which have, you're assuming that over the lifetime of that travel, they are the same frequency. They're not changing in any. So that
they can
is-
be redshifted,
they
for
can-
example, but yeah, it's
Okay,
a frequency that then gets redshifted as it propagates.
right. So,
Wait.
okay, so that's in the modeling itself.
Yeah.
And you can have sources which are not monochromatic, but they change with time, and that will be included in this anyway.
You could,
Right.
yeah. We will be operating in the regime where they are monochromatic as well. get to, but you don't have to.
Sorry, do
Yeah.
you expect a dipole component due to the movement of the galaxy, whatever?
So those are things you would have to remove. So when you're modeling your pulsar, if you don't properly account for the relative motion between you and the pulsar, you would see a dipole. But so you need to do that very precisely, and people remove that. And they measure all of the multiples, and you can see in PTA results that they properly account for the removal of the
I
dipole.
don't mean
Yeah.
the movement of pulsar, but just the movement of
Oh, of the
respect to the Yeah.
well, you would, I guess the movement between us and the
just the
relative, um,
and whether
I don't-
that's aligned with the CMB dipole, stuff like that, is that something?
I don't think, yeah, I don't think that's a concern.
But it's
Yeah, I think you
interesting.
would, yeah. Yeah, I'd have to think about how you would see that here, yeah.
So related, so you only see the relative motion between the pulsar and the Earth, right? So you probably won't see the CMB, us moving with respect to, because we are moving together with the pulsar. I don't think we have.
Mm.
Ah, okay,
That's-
okay.
Yeah, it's just relative.
Cosmological.
Okay, so that makes
Yeah,
sense.
that's a good point, actually,
Okay.
yeah. Right, so the first non-trivial moment in this case is the variance, and you can look at the correlation between your timing residuals. And the presence of a background should be the only correlated component that has the particular features described by, you can describe the particular ways in which these pulsars are correlated. So if I take the expression that I had before and I compute the correlation, the angular correlation, or I can compute the correlation between timing residuals of two different pulsars, you can describe this by an angular part, which is known as the Hellings and Downs correlation, and then the energy spectrum of your source. And this quantity, you also heard a lot about it yesterday, and it's related to the characteristic strain of your sources or the equivalently the energy density and gravitational waves. And for you to do this calculation, you can make several assumptions about the properties of this background, like that they are monochromatic, that they are unpolarized, that there's no angular correlation between your sources, and that it's isotropic. So there's no dependence on any angle here.
So about the angular delta function there, so as these are waves that are propagating between the pulses and us, is there an area of overlap of the same wave between two different sites, which breaks this assumption, or it doesn't?
This
It's
is,
such a small overlap that it doesn't matter.
well, this is, so omega is the direction of propagation of the gravitational waves, and you're just saying that they're not correlated, like clustering is negligible, yeah.
I was thinking about the direction of the.
So the direction of the pulsars only come into
It's only-
this,
yeah.
so it's just theta AB. So your yeah, the
Yeah.
Hellings and Downs only depends on the correlation between these things. And you can compute this exactly. It just depends on the degrees of freedom allowed in GR. These determine these angular patterns, and the Hellings and Downs is just an integral over the entire sky of your antenna beam pattern. So this is the characteristic signal that you get for gravitational waves, and it should not be mimicked by anything else. In particular, nothing that is correlated among your pulsars.
Can you show an expression for capital F?
Yes.
So this comes from GR.
Yeah, and by computing the deviations in your timing residuals, and this just depends on the vectors in the direction of your pulsar, and then in your polarization tensor, which just depends on your degrees of freedom in GR.
So if I have
Yeah.
a modified gravity model with more polarizations.
Yep.
It's time and now will look different.
Yep, you can compute other correlations and modified gravity, yeah. Okay, right, so pulsar timing arrays sit at the lowest frequency end of your in the realm of gravitational wave detectors. The frequencies that you're sensitive to depend on the lowest end, on the total observing time that you spent looking at pulsars, and then at the highest frequencies on the cadence at which you go back and try to measure the period of these pulsars, which is typically on the scale of weeks. Now, the sources that fall into your detector are expected to be presumably supermassive black hole binaries. And you also have more speculative sources that there's definitely a large community that is interested in this. And maybe some of you are part of that, given the nature of the workshop. There's a very long list of potential sources. And for example, you can read more about this in New Physics from Nanograph. There's a very long list of different models that are compared to the data. So I think even if you're mostly interested in these things, you still need to deal with the existence of supermassive black holes. And that's what I'll be focusing on. So in terms of supermassive black holes, this is just to give a sense of the scale of your detector and then of your sources. So the pulsars live in the galaxy. They're roughly kiloparsecs away. Your sources are at cosmological distances, so say hundreds of megaparsecs to gigaparsecs. And the frequency that they emit in is twice the orbital frequency of the binary. And by just plugging in Kepler's law, you can show that, for example, a 10⁹ solar mass black hole at a separation or an orbital separation of subparsec, like 0.01 parsecs, will be producing gravitational waves at 10 nanohertz. So this is kind of a representative source that I'll be discussing in this talk.
So why specifically dense supermassive? Can't you have something like closer that redshifts less?
You can have something closer. The problem is that as you look at like smaller, are you referring to like smaller mass things or yeah? So the gravitational wave signal scales with like mass to the 5/3. So as soon as you start to decrease the mass, you quickly become kind of irrelevant for the signal. Yeah. Okay, so
But I think decreasing the mass also makes the frequency be a different frequency on quadrant, right? So let's say different frequencies.
yeah, you could imagine like lower mass things that are like at some larger separations, and there's some trade-off, but yeah, at some point.
The lower the mass, the smaller the period can be for the touch.
Yeah, but these are very far from merger. The sources are very far from merger. The frequency is set by the separator.
Yeah, we'll get to that. Okay, so the expected sources are supermassive black holes. So I'll comment a little bit on what we already know about supermassive black holes. So we know about supermassive black holes that live nearby, by which I mean within the local 100 megaparsecs, where you can get pretty good measurements of their masses. And there's a series of well-studied scaling relations between properties of the host galaxies on the x-axis here. This is the velocity dispersion of the galaxy and the mass of the supermassive black hole. People do this with other galaxy properties, but they're basically labels that you're applying to the galaxy and seeing how this corresponds to the black hole mass. Beyond our more local universe, you're kind of limited to seeing supermassive black holes that are actively accreting and shining as very bright quasars. And one kind of simple way to think about what you're learning about supermassive black holes from quasars is through this Sultan argument. So basically, the idea is that your quasars are powered by accretion onto the central supermassive black hole. So as, say, some blob of gas is falling in, it radiates a certain amount, which you see as the luminosity of the quasar, and whatever's left falls into the black hole. So there's a relation between the total integrated luminosity of your quasars and the mass that it has been accreted into your black hole. So if you integrate the observed quasar luminosity function over all luminosities, that's basically telling you what the mass density accumulated in black holes is. So there's a neat relation between these things. Yeah.
What is the uncertainty in the efficiency of this process?
Yeah, so this is all just dependent on this radiative efficiency, and it's not a very well-known quantity. So mostly what you want to do is if quasars if the black holes that power the quasars are the remnants that we see today, you basically just match these two things and you pick a radiative efficiency such that's true. Like there are theoretical predictions about it, but they're not very constraining.
So that's
And
with obscured rose in the field.
yeah, so the obscured fraction comes into how you're correcting this quantity here. So if there are more obscured quasars, then you're not accounting for that contribution to.
So it has to be the true bolometric luminosity that you have to infer.
Yeah.
By decomposing all the absorption from everything, pretty much, right?
Yeah. So from pulsar timing arrays, you're learning about the supermassive black holes that are in the process of merging. And the basic story is that pretty much every galaxy that we look at has a central supermassive black hole. Galaxies merge, supermassive black holes probably then merge following that. People don't know really well how this happened. There are a lot of question marks here. But if this somehow gets solved, then they arrive at these subparsec separations that's where you see them in pulsar timing arrays. And I guess just a thing to note is that yesterday we were talking a lot about this part of the gravitational waveform, which is what you see in LIGO, for instance. But with PTAs, you're seeing this very early in spiral phase. So they're very Newtonian. They're pretty much monochromatic in frequency. And that's where we expect to be seeing that.
The question mark in there?
So, I don't know how this goes, but for what I know that there's in the future experiments such as LISA, one expects to have like inspiral signals also from, I don't know from if this is compact enough to observe that, but is there kind of some promise of being able to combine PTA signal with something that can be seen also in next generation of radiation wave?
So LISA, the sources that are, so LISA red is at higher frequencies. You would be seeing them, here.
Okay.
But the supermassive black holes have to be a smaller mass, basically. The things that you expect to see in LISA are like max of like 10⁷ solar masses, whereas in PTAs, you're dominated by billion solar mass black holes. And those merge, it kind of in between
I thought that you could see like
PTAs.
previous inspiral phases, but I guess they.
No, so in principle, your signal in PTAs can have contributions from 10⁷ solar mass black holes, for example, but they're going to take millions of years to evolve. And then you're also not really dominated by them in PTAs, while in LISA, they're like your main, some of your main sources, yeah.
So is there an expectation value of the distance between them?
Between the binaries?
Yes.
Yeah, so that's this quantity here. This is the orbital separation. So, I mean, it comes back to Kepler's law, basically. And you can see, given a mass and the frequency that you observe it, what is the orbital separation that they would be in? Yes.
Sorry, so like you said that the signal with nanohertz, if they were about 0.01 or 0.1 parsec away from each other, but then you have to assume that nature can get these black holes. It's like a natural prediction that they should be this close for the signal to be in this band anyway. And is this something that is well understood?
Well, I guess you could make you could flip the statement and say, if we've seen gravitational waves and we assume that they're produced by supermassive black holes, then you've solved the final parsec problem, right? Somehow. But I mean, I think people have ways to get around this. I don't know that even most astrophysicists agree that this is still a problem. It's just like, what kind of circumbinary disk you need to have, or like, these types of things.
Yes, like in the absence of the results.
Yeah.
This means that they actually never solve, like nature doesn't solve the.
That's what Scott says, right? I mean, I've had this conversation with Scott Tremaine, and to him, the final parsec problem was never a problem until you detected gravitational waves, because things could have just never merged and stalled forever. Anyways.
So this would only be a problem if you see a lot of those mergers or a lot of those objects, right?
Yeah.
Which is, I mean, will be good.
Yep. Okay. So I just also wanted to say a bit more quantitatively how these three things that I just mentioned are related to each other. And you can basically describe the evolution of the supermassive black hole mass function through a continuity equation. So psi here is the mass function in black holes and the evolution of your black hole mass function over time. You can write mass conservation over here. This is just the divergence of a flux, basically. And you have two other terms that I'll get to in a second. But so from your scaling relations and from galaxy catalogs, you can infer the mass function of black holes today. So choose some label for your galaxy, say if the velocity dispersion, you can take a galaxy catalog, apply this label, count these things, and then see what the corresponding masses are. And from that, you can infer a mass function today. And this is basically telling you a boundary condition for this. From this middle part, this is again, as I've, I guess, mentioned it in a bit more detail previously, the change in the mass function from accretion is related to the quasar luminosity function. And so from that, you can get an observational handle on how your mass function is evolving due to mass accretion. And then these last, these last two terms are basically, I'm not going to write them out explicitly, but they're basically a creation and a destruction term from mergers. So you're creating black holes in the limit where mass is conserved. You're basically just redistributing your black holes from smaller mass things to higher mass things. And you have some creation term, which captures how two smaller mass black holes merge to form a black hole of your final mass n, and then a destruction term where this black hole of some mass n merges with some other thing and produces a mass, some other mass. And this is what the pulsar timing arrays are kind of telling you about this evolution. This is something I'm currently working on, but I won't say anymore in this talk. But basically just from the existence and the measurement and this measurement, if it is produced by supermassive black holes, you can say something and kind of complete this picture about the evolution of supermassive black holes in the universe.
Sorry, is there any knowledge about the speed of which there are orbital?
Yeah, I guess from just like basic orbital mechanics, right? They're just two binaries
But
self-gravitate.
you don't know anything about the speed.
You do, yeah. It's
Kepler rule.
this is Kepler's law, yeah. Yeah.
So, for LIGO mass, LIGO masses, the energy is not conserved by a large fraction, like large fraction of the mass go away in gravitational wave. Right?
5%, no, it's like a pretty small
So,
fraction.
but is this the same for the supermassive black holes?
Mhm.
It's not the end of the scale.
Yeah,
Yeah, but I have a question. So
Yeah.
suppose that this happens 100 times, then 5% over 100 times is not.
you do get it.
bit.
You do get, yeah, you if it happens 100 times, you do get, I guess, you accumulate it to some extent. Yeah.
The average number that you expect.
It's not very large. Yeah. Yeah. Okay, so this has been detected, right? We've seen gravitational waves from pulsar timing arrays. This is again basically the two ingredients that you have here for your that you can measure are the angular correlation, which is the Hellings and Downs, and this is just an example from nanograv, from the nanograv results. So this is Hellings and Downs curve, some measured points, and the energy spectrum, which, as I mentioned, is related to strain amplitude and your gravitational wave energy density. So these are, yeah, some recent measurements from this, and multiple pulsar timing array collaborations around the world announced this simultaneously about a year ago, a year and a half ago. So there was the European and Indian PTA combined their results, Nanograv, and which is a North American collaboration, Parks in Australia, and then the Chinese PTA, they all simultaneously announced evidence for this stochastic background. So I'll focus mostly for the rest of the talk actually on just this energy spectrum and how we can interpret it. So what is this energy? What does this energy spectrum depend on? This amplitude of your correlations. So it depends on the energy density per log frequency in gravitational waves. And this is basically the sum over all binaries times the energy spectrum that they emit. And again, this is something that you can predict very easily from just equating the change in the orbital energy to the power emitted in gravitational waves. And that and Kepler's law, you can predict this universally. So it's a very well-known quantity, and that's why there's a very strong prediction for what the power law of the spectrum should look like. You can have some deviations from this. For example, if your background is produced by discrete sources, you will have variations frequency to frequency because the sources are all monochromatic, and if you vary the number of sources, you can have these fluctuations. And I'll talk about this in a little bit in the kind of second part of the talk.
But
Yeah.
you're discrete, you're going to mess up the halogen count flows.
You can have some variations in the limit where you have many sources or uniformly distributed pulsars in the sky. You always recover the Hellings and Downs. But if you have ununiform sampling and discrete sources, you can, depending on where your pulsars are, you can have some deviations in the Hellings and Downs. That's true. Yeah.
What defines the cut between environment and discrete? What's the scale?
So this is a cartoon, and so it's not really a realistic rendition of this, but whenever the energy you're losing from so if you have, say, a disk or some other astrophysical interactions, you can shrink you can change the orbital, the binding energy of the binary through other means that are not gravitational waves, right? So this power law assumes that your energy loss is all from gravitational waves, but if you have some other way to shrink the binary, then you will not be emitting gravitational waves and you'll suppress this. So that the scale is just whenever one equals the other transition.
So you're saying that the power law is well known because the energy spectrum.
Yeah.
But not the altitude because the binary merger rate density is not.
Exactly. So there's a strong prediction for what the power law should be, but so the uncertainty here is mostly in what this amplitude is. Okay. Right, so how do we understand what the amplitude of the background should look like? There are kind of a few approaches that you could go about modeling this. One very popular approach is to try to connect it with things we think we understand. So for example, you can try to connect them with like the halo merger rate and somehow populate your halos with galaxies with supermassive black holes and assume some kind of delay time between these things to merge. And then eventually you can get a prediction for the merger rate of binaries as a function of redshift. And I think it's pretty clear how you accumulate a lot of errors, right? How do you know what the connection between supermassive black holes and galaxies is as a function of redshift, or what the delay time even is? So yeah, I think it's pretty clear how you fold in a lot of uncertainties by doing this. But so there's an alternative approach, which was pointed out by Finney in 2001, not by us, but that really simplifies how you model this. And the basic idea is that you can think of the supermassive black holes that exist today at redshift 0 as potential remnants of previous mergers. So if I look at the mass function today of single supermassive black holes, which, as I've mentioned before, is something we can estimate from observations somewhat directly. Say all black holes merged once in the history of the universe, then the number of single supermassive black holes is just equal to the number of binaries as a function of their total mass, assuming that mass is conserved. So, yeah.
Just have one question. I mean, when we say that we know the mass of the black holes inside these galaxies, even nearby ones, do we actually know that they are one black hole and not just maybe two in many cases? Can we know?
So you're only inferring the potential, right? You're taking a galaxy and you're describing the potential of a point source and of the galaxy. So you don't really know.
You can't really know. You can't even know if it's 5 black holes inside.
Yeah, but
Some crazy
we'll see
orbit.
that this doesn't really make a difference, actually. Yeah, it doesn't really matter if
Doesn't
they're,
matter.
how many they are, yeah.
Can I rephrase it? So it would be fair to say that the fraction of supermassive black hole that are in pairs can be anything from 0 to 1, as far as we know.
Yeah. But as you'll see in this prediction, it will not make a difference.
That's why
if
we
we're-
don't know.
Yeah.
To make a difference.
Yeah.
No.
Yes.
What's, and what's the price you pay to have the second picture? Because you're somehow assuming that all black holes we see come from mergers, which assumes somehow, okay, it's kind of like, these three mergers.
Yeah.
So,
The goal is to have an upper limit. So here you will get some prediction of what you think what the like fiducial values say will be. Here you'll have to make some assumptions, but it becomes really clear what the upper limit is. But you're not really predicting, well, you have to by hand make some weird. Well, let me get to the actual argument and then we'll see.
Just a
Yeah.
totally ignorant question. Can a super duper hydrosim help?
You're still limited to whatever assumptions you make to go from your galaxies to your black holes, right? I think these can help each other, right? Like, from this argument that whatever thing you put into your simulation needs to produce the correct mass function today. Otherwise, you're going to be getting this prediction wrong, right? So it helps you pinpoint like what benchmarks you need, for example. And what is the maximum, like you can tell if something's going wrong, right? If your maximum here supersedes. this maximum.
Black holes are formed in this hydrosim, but I'm not
They
sure
are.
about supermassive.
Well, people try to simulate them, but they're very difficult. So a lot of the community does that precisely. And there are many options that like from Illustris, there's this simulation called Astrid, from like Universe Machine.
But
there's
in
like
every single case, they
Trinity.
put them by hand.
They
They
put-
don't really simulate any.
They simulate like the growth, and how like some of them have like particles that fall into the black hole.
But
And they
it's
have
also
some
the
prescription.
sublimation. No, but
Exactly, yeah.
So at least, I mean, I know this example of the Ketchu code that implements also some kind of post-Newtonian instance. Actually tries to solve more like the fine force parsec problem with three body interactions in a very small region around black holes and things like that. But still, it's true that it's very specific. But I have just a small question. I didn't get that in the second model, you're saying that you need this the black hole mass function. But then I didn't fully understand how then if it's not clear if these unresolved systems, there's many of them, you still get the answer right.
Let me just tell you the following slide, and then it'll become easier to explain why it doesn't matter. So, so if I take the second picture, I can now rewrite this expression only in terms of the single mass function today, where I've still had to assume some redshift distribution for when these mergers happen and the symmetric mass ratio for these distributions. But I think this makes it clear, like, this leaves you nowhere to hide, right? Like you can see exactly what your astrophysical knobs will do. They'll change these values, and you're just then tied to whatever the single black hole mass function today is. So basically, if you have some contribution, say these binaries today, say they are binaries, say they are in the PTA band also coincidentally, that's just adding a redshift 0 contribution here. So you can always just take this upper limit to be for redshift 0, basically. Does that? Okay. Right, so you can do this. You can take the observations that I mentioned before from the scaling relations and from the galaxy catalogs, and you can predict what your mass function is. Here's a few examples from velocity dispersion and from stellar mass, and the resulting mass function. And then this is showing the characteristic strain that you get from just this assumption of a single merger. And the thing we're pointing out here is that basically they overwhelmingly show up below what PTAs are measuring, which is strange because there are a million ways that this prediction could be lower, but there is just an upper limit for how large these things could be. So this assumes some fiducial PDFs, but you could also just take an upper limit and Yeah, so we, we were interested in this discrepancy that appears on the strain. So here, for example, this is the prediction for the strain amplitude squared. And you can always take an upper limit by just picking redshift 0, mass ratio to 1/4. And then here we choose some distribution that leads to these values. I guess another thing to note is that it's very insensitive, for example, to your redshift distribution because of how small its power is. Like you have to change your redshift distribution by a very large amount before you actually change this prediction very much. Okay, so this is, I guess, one of the main things that we point out in this work. And so, okay, right, can it be, I've assumed that they've all merged once. Well, how much more can you get by just assuming that they merge multiple times? And so you can do, again, a very simple calculation of just suppose that they merge an infinite number of times with equal mass companions and they all happen instantaneously. You can write the corrections to your strain amplitude for multiple mergers. And basically because you're always merging smaller and smaller black holes as you split them up, this always converges to like a pretty small number. So for example, if you take this, if you write this as the series, you're saying that basically at each previous layer, you had twice as many black holes, but that were twice half the mass. So you get this 2 to the minus factors n. And this converges basically to a shift in about 60% in the characteristic strain. You could boost this by not assuming that they conserve mass, but this 5% only makes this like, I don't know, 80% or something. It doesn't change this picture very much.
Right.
Yeah.
And does the picture change if you assume different values for the mass ratio?
No, so this is the maximum you get. Well, yeah, so if you do this, or if you include different mass ratios, basically with a different mass ratio, you start off with a smaller value here, but the boost that you get is the same. But yeah, we look at this in the paper as well.
Sorry?
We look at that in the paper as well. But no, so the answer is no.
It will take longer, no? So you will have less mergers, it will take longer if the mass ratio is unequal.
Yeah, here we're just assuming that they happen instantaneously and just take this upper limit of like an infinite number of mergers. But if you were to assume a time delay, and presumably it's larger in that scenario, yeah, that would also complicate things.
So like what do you lose due to the time delay, even if you don't assume that, you don't consider that, like what do you lose in that the amplitude of the gravitational waves is smaller, you don't gain it by the fact that like you can account for more mergers that way?
No, well, if you start off with if you do a smaller mass ratio, you start off lower and you can have more mergers to make up for the fact that they're not equal mass. But anyway, ultimately the boost is the same that you get, yeah.
So maybe I missed it. So this
Yeah.
doesn't depend at all on the Sultan argument with some known total volumetric luminosity of all the quasars in the universe. That
No.
just doesn't come in anywhere.
No, later we compare, later we use that as a point of comparison, but this is completely independent. This is just the mass function today versus the supermassive black hole or versus the PTA amplitude.
What about accretion? Is it being considered somehow?
So we're not including accretion here. If they did grow by accretion, then your mass would be lower earlier on, and so you would reduce the signal. But we're not including that.
That's a good change of this. There is some expectation for them.
There is. So when we were writing this paper, we thought that it was a very conservative assumption to neglect accretion. In a more recent work, what you can see is that these very massive, supermassive black holes accrete at way earlier redshifts. So the quasar luminosity function for your highest luminosities just peaks at redshift like 2, 1.5 or something. So that's when these things are mostly growing by accretion, whereas mergers, you just by like hierarchical structure information, right? Like mergers of very massive things just will happen in the very late universe. And so you have this like separation of epochs basically. So most of the accretion is happening at higher redshifts. Most of the mergers are happening at lower redshifts. So it's actually not interfering.
Yes,
Yeah.
so of that mergers of smaller masses at higher redshifts, which are redshifted inside the band of PTA,
Yeah,
these are also all included in there. I mean,
Yeah.
you're taking this to redshift as long.
but it really doesn't matter.
It really doesn't.
It really doesn't matter because, again, your mass, there's another plot that will come up. But you're very just dominated by a characteristic mass, which is a few times 10 to the 9. And those merge at very low redshifts. We assume the redshift distribution, but it's pretty sensible that it would just depend at low redshift. So at high redshifts, as soon as you go to smaller masses, it really doesn't contribute to the background almost at all.
Sorry to bother with, so in the nanograph paper, they also compared these holodeck simulations, and they also find this 2 sigma difference. So how shall I read this? Like this 2 sigma you find there is almost the same as they find, what's the?
They don't find, they're way more conservative about how they frame this. They don't, so it's not, so if you just compare it with a simulation, why are they different, right? What about the simulation is producing this? And I think it's just that the simulations are calibrated on these observations and then they agree. But I guess the point is that it boils down to the mass function today. Yeah. I think the simulations have more error too. And
So
like, I don't think the statements are so strong in.
this 2 sigma you see there, it's basically, you agree with these 2 sigma?
Sorry, which 2 sigma?
Oh, sorry, if you go to the next one. Compare your lines with the black ones of nanograph.
Yeah. Where's the simulation though?
No, I'm just thinking like, there is no simulation there, right? But
No.
you see a 2 sigma difference between nanograph and what you would expect from your results, right?
Yeah, so actually the point of this plot is that as you include multiple mergers and you can include time delays, we'll boost this. And then the absolute maximum that you can get by just taking this limit to infinity is this gray point here. So this is like the absolute upper limit that you get from this mass function. And this is at this like 90% bottom error bar from nanograph. So you really need to push all of your assumptions to the absolute maximum to even get to this like bottom.
So what then can explain nanograph this much?
So, I mean, if we double the number of, if you get the mass function, because the anchor of the mass function is at redshift 0.
Yeah.
Is that it, right?
Yes.
So if you say that is wrong by a factor of 2,
Mhm.
that fixes that, but then you have. to
Oh,
split,
so
or
this
no?
is the strain. It's a factor of 2 to 3 and something in the characteristic strain, but the characteristic strain squared is proportional to the mass function. This is a factor of like 4 to 10 in the number of black holes.
Okay.
Yeah.
So we would have to say that not only there's a black hole in every galaxy, but there's
Yeah.
still also black holes just scattered all over the place, which we haven't seen.
Yeah.
Something like this,
Yeah.
which is kind of crazy. Okay.
Or one of these
Or
measurements is
Yeah,
wrong.
or the measurement.
Yeah. Okay. So I've almost said everything that is coming up in these slides just now, but I'll still also talk about them. Right. So the characteristic strain, if you plot the kernel in mass, you can see that this is very peaked at some characteristic mass. So this, so for the local mass function that we use, this value is about 3 times 10 to the 9, and that's pretty much the only mass that matters here. If you look at the black hole mass density, which you would get from the Sultan argument, this is sensitive to a bit lower masses. And so, you know, what I was arguing here, I guess just to not lose the thread, is that because you need these very extreme assumptions to get to this lower bound, this is probably not the only explanation for what's going on, right? So we look at what we could be misestimating, for example, from the mass function. Like, how would you need to change this so that you would reproduce the value seen by pulsar timing arrays? And so, right, so one point of comparison that we use is the mass density from the Sultan argument. And the basic conclusion is that if you want to not change this by a very large amount, you need to change the high mass tail of your black hole mass function. So you could just ask to have like 10 times more black holes, or you could shift the tail of your mass function a little bit and still that would also work. And from the point of view of the PTA, those are indistinguishable, right? Because you're just measuring this mass to the 5/3, average mass to the 5/3. And so we do, I'll try to go quickly now so we're not here forever. We look a bit at how you would need to change the mass, the parameters that describe your mass function so that you would recover this, the value measured by PTAs. And if you're just interested in this high mass tail, basically the relevant quantities that you can vary are, for example, this like turnover in some Schechter function that describes your velocity dispersion, or the scatter in your scaling relation. And this is showing the range of parameters that you would need for these to be consistent. But basically all you're doing when you say I choose one of these sets of parameters, x1 and x2, and I wanted to ask what kinds of sigma and black hole mass are 50 and 90% of are contributing 50 and 90% to my characteristic strain. These are these contours. And you can see that all you're doing is that you're asking for your sources to correspond to black holes that we've never seen in our local universe, which, I mean, of course, right, because the predictions are disagreeing, but effectively that's all what you do when you're changing these parameters around.
Is there any way to find those black
People haven't so far. And so there's, for example, this massive survey, which is led by Jenny Green and by Chung Pei Ma, which tries to measure the massive end of these supermassive black holes in our kind of local, like few hundred megaparsec universe. So they have the sample. It doesn't seem like these suddenly become consistent with each other, but it's I guess ongoing work. But yeah, so the basic conclusion is that if you just want to boost the amplitude, that corresponds to about 4 to 10 times more black holes. Or if you're changing the shape of the mass function, you need to change this peak mass that contributes by about an order of magnitude. So you need your, instead of 3 times 10 to the 9, you need 3 times 10 to the 10 to be your dominant black hole. Those are the requirements. Okay, I'm going to shift gears a little bit. This was the last part of the talk. This is, if we want to break for lunch, this would be a good point. I'm just putting it out there. Yeah.
Fine if we keep it for the, what's the, well,
This would take probably uninterrupted, maybe like 15 to 20 minutes. But I don't think, yeah.
So we, I think 20 minutes is fine. And then, okay, let's go. I promise no questions.
Have a discussion of.
We just bring the broomstick back after lunch and then just
Yeah. Okay, so we discussed this after lunch. Yeah, and then we give a proper.
Yeah.
Yeah.
Lots of questions.
Right. So thanks, guys. There was tons of questions. Any urgent questions now? One last. Please.
Oh, yeah, sorry.
You're focused on the amplitude, right?
Mhm.
But the power law doesn't really fit the PTA, is that right? And so then, as far as I understood, you're not reaching the amount you needed to in the end. So wouldn't be like a rational or good way of looking at the results is that there are other sources like primordial black holes, something that has to be summed with this.
Yeah.
So you have to combine supermassive black holes with all the different kind of sources and.
So if you're very confident about this argument, that would be the conclusion. But I think there's still some, I guess, digging that needs to happen before this is a.
And the measurable.
Yeah, I mean, like you need to be very confident about both measurements to be able to claim this, right?
How-
But that would be the. That would be the.
And how we have to combine the, like have supermassive black holes and like, let's say like something coming from the early universe. How do you combine just summing the two spectrums or?
Pretty much, yeah, you have
Yeah.
two contributions to the background. Yeah,
Just leave it?
they're additive.
Okay, so thanks, Gabby, again.
Y ahí
I think especially it's directions.
Don't worry, don't worry. It has to make some time there. So So this So I think it's define smart, it's making there's no actual limit of like 30 views that have to clear. Yeah, I mean, and then I'm starting to worry if it goes big, how many of the demandados and